Hello everyone and welcome to OneClass. My name is Jeff Krause and I have a PhD in physical chemistry or chemical physics. And today I'm going to run through a few undergraduate level, high school level physics questions. So here's our first one. So here we see So the question is, a certain orthodontist uses a wire brace to align a patient's crooked tooth, as in the figure. The tension in the wire is adjusted to have a magnitude of 18 newtons. So there's a vector diagram here, which also gives us an axis system. And our tensions are written like this. And it tells us that there's the angle in here is 14 degrees and 14 degrees. I'm just going to erase that. Okay, so it asks us to find the magnitude of the net force exerted by the wire on the crooked tooth. Okay, so our only forces acting right now are the tensions, and we'll want to find them in both the x and y direction. So I'm just going to expand these triangles out here. Right, so we've got y, x, and 14 degrees, and I don't know why I put y and x, especially on the wrong axes, so that would be tx and ty. Okay, so just using trigonometry, so that should be a right angle triangle there. Tx is going to be t cosine of 14 degrees, and ty is going to be t sine of 14 degrees. And I haven't put any signs on here, but we can do that with when we look at our force equation. So here we have F is going to be Fx x hat plus Fy y hat. Fx is going to be all the forces in the x direction. So that would be, we're going to get, I'm going to call that T1 and that T2. But T1 is equal to T and T2 is also equal to T. But just to differentiate them. So we're going to get T1, T1x plus T2x. T1x is just going to be, it's acting in the positive x direction. So it's going to be T cosine of 14 degrees, and T2x is acting in the negative, so it's going to be minus T cosine of 14 degrees. And so these two are just going to cancel, so it just equals 0. Now Fy, if we look here, they both act in the negative y direction. So it's going to equal T1y plus T2y, which is going to be minus T sine of 14 degrees minus T sine of 14 degrees. which then equals minus 2t sine of 14 degrees, which plugging in some values here, t is 18 newtons. And so that's minus 8.71 newtons. Oh. Okay, and so it asks for the magnitude of the force. So our total force is just minus 8.71 newtons in the y-hat. But our magnitude of our force is the square root of this squared, which in this case, because there's no x, it basically just removes the sign. So 8.71 newtons. So our net force acts in the negative y direction, pulling the tooth in, while the magnitude of the force is just 8.71 newtons. Okay, let's look through the solution here. So net force in the x is 0, net force in the y is minus 8.71, so that looks good. And okay, it's missing the magnitude, but that's okay, so the solution is correct. Magnitude of force would be 8.71 newtons. Okay. So for the second one, I'm just gonna draw the figures. So it says P720. So we have A going to B along a straight path, and there's a bead, and then we have a curved path with another bead. Okay, so for the straight path, first we have our mass is 25 grams. The length of the wire is 0.600 meters, and the height from A to B is 0.200 meters I used, but I just realized it doesn't really say, but it must be meters. And we have a constant friction force of 0.0250 newtons. So we could easily, so the first question is just what is its speed? So if VI is 0, what is VF? So we release it from rest at A, what's its speed at B? So this is quite a simple question without friction. So we can use energy conservation, so our energy initial would equal our energy final. I should put without friction. But with friction, it's going to lower our energy by the work. So our final energy is going to be our initial energy minus our work due to friction. And our work due to friction is just going to be our frictional force times our distance, which is 0.0250 times the 0.600 meters, which comes out to be 0.015 newtons. Okay. Okay, so that's how much we're going to lower our energy. Now we need to fill in kind of these other terms. So our initial energy is just our gravitational energy, so it's going to be mgh. Choosing the zero of gravitational energy at B, so that would be 25 grams times 9.8 meters per second squared times 0.2 meters, and then multiplying by 1 kilogram per 1,000 grams to cancel the grams and give us a value in kilograms meters squared per second squared, which is a joule. So running through all of these values, we get 0.049 joules. And then our final energy is going to be purely kinetic. But we can solve for it now. So our EF is 0.049 joules. Oh, I made a mistake on my work, just a slight. So a Newton meter is a joule, not a Newton. So that should have been joules. All right. And so our final energy is going to be this 0.049 minus our frictional work, which is then 0.034 joules. Our final energy is purely going to be kinetic energy. But we can write it as kinetic plus potential. But our potential is 0 as mgh is equal to mg times 0, as we've chosen our 0 of potential at B. And so kinetic energy is just 1/2 mvf squared. And so that we can now put these two together and say that 1/2 mvf squared is 0.034 joules, or vf is 2 times 0.034 joules over m square root. Plugging in some values here now. 0.034 joules over 25 grams times 1,000 grams per kilogram, just to put it into the proper units so we can cancel out our joules. And remember that a joule is a kilogram meter squared per second squared. So this kilogram will cancel with this one, leaving us with meters squared per second squared, which after the square root will be in meters per second, which is our speed. So now this is square root of 2.72 meters squared per second squared, which gives us 1.649 meters per second. And just looking for, so everything's got 3 significant digits. So I guess these should have all been 0, but whatever. So this is 1.65 meters per second with significant digits. So there's our final speed. And then part B of the question just asks if a bead is released from rest along this path or this path, which will arrive at B faster. Now this one's a little tricky because without friction, the lower bead should arrive faster as it reaches its terminal velocity at a higher rate, therefore traveling in the end along B faster. But with friction, we now have a longer path, and so without being given the exact path length, our work due to friction will increase as our D increases, which means that our EF, which equals EI minus our work due to friction, so our EF is going to decrease. So our final velocity will be less. And so presumably it's going to travel along the lower path slower because the path length is higher and our energy is lower. Yeah, so checking through the solution we have here. So we're given the mass, the path, and the height difference is our frictional force. So we can get our initial energy as mgh, which comes out to be 0.049 joules. Energy loss due to friction is 0.015, which is just our force times our distance. That means our energy, our final energy is just that minus our initial energy minus our work due to friction, which comes out to be 0.034. That equals our final energy, which is just kinetic. So we can solve for VF, and if we do, we get 1.65 meters per second. And then, for part B, the mass and friction is the same. So the path length is now larger for the lower path, increasing the energy loss. So it reduces the speed of the lower bead, but which arrives first is hard to say, I would say, but I presume the top path should arrive faster. So I presume the top path should be faster. So let's say the solution is correct. Okay, here we've got 3 masses aligned as I'm going to draw them here. We're given an axis system. Like this, and they're all connected. And the assumption is that the rods are massless, and we've got a 200 gram mass here 160 gram mass here, a 350 gram mass here, and we're given that this is 12 centimeters and this is 10 centimeters. And it asks for the x-coordinate of the center of mass and the y-coordinate of the center of mass. So to solve for a x center of mass, we just sum up all the masses times the x-coordinates and then divide it by the total mass of the object. So doing this for this problem here, so we've got this x-coordinate is going to be 12 centimeters. So for here, so numbering these from 1, 2, 3, our x1 is 0, our x2 is 12 centimeters, and our x3 is 12 centimeters. And so then the x center of mass is just 200 grams times 0 plus 160 grams times 12 centimeters plus 350 grams times 12 centimeters, all divided by 200 grams plus 160 grams plus 350 grams. So continue. So this is just 0, and so this is 1920 grams centimeters plus 4200, all divided by 710 grams, which is 6120 over 710 grams. Grams are going to cancel, and so our x center of mass is just 8.62 centimeters. And now for the y center of mass, we need our y coordinates. So again, looking at this and our axis system, we have y1 is 0, y2 is 0, and y3 is 10 centimeters. And so we have a similar equation for our y center of mass. So it's just going to be the sum over all the masses times the y coordinates over the sum of all the masses. So our x center of mass, so our y center of mass is just going to be 200 grams times 0 plus 160 grams times 0 plus 350 grams times 10 centimeters, all over the 200 grams plus 160 grams plus 350. And so then this is equal to 3,500 grams centimeters over 710 grams. These grams will cancel, giving us 4.93 centimeters. And so our x center of mass is 8.62, and our y center of mass is 4.93. Okay. And so we just find our center of masses by summing up the masses times the distances. Here we have a little table, but in the end we get 8.62 for our x and 4.93 for our y. So that looks good. right, so now we've got a chandelier. I'm just going to draw it. And we've got this, and then the chandelier is hanging from here. Okay. And now the mass, and it asks us to find each of the tensions. So we've got a T3, we've got a T2, and a T1. And I guess there's not really a directionality there. And just to draw these up. We've got a theta1 and a theta2. And theta1 is given as 37.0. Theta2 is given as 64.0. The mass of the chandelier is given as 125 kilograms. And it's asked to find what the mass, or what the tension is in each of these strings. So we've got 1, 2, and 3. So considering just where the chandelier, so looking at this static equation, we have our force due to gravity, which is just mg, must be balanced by the tension force, tension 3. And so we can say that our force equation here is just our gravitational force. I guess I'll use up as positive, so minus our gravitational force plus T3 is equal to 0. So then that means that T3 is equal to our gravitational force, which is 125 kilograms times 9.8 meters per second squared, which comes out to be 1225 newtons. So there's our T3. And now expanding for T1 and T2. So I'm just going to kind of redraw here. So at this point, we have T3, T1, what did I call this? T2, and T1 over here. And that angle is 37 degrees, and that angle is 64 degrees. Okay, so here now we can separate into our components. So our force is going to be Fx x hat plus Fy y hat. And because nothing's moving, this is going to equal, well, it's always going to equal ma, but because it's not moving, it's going to equal 0. So that goes to 0 because there's no acceleration. So now looking at our x component forces and using this as our x direction and this is our y direction. Our x component forces are going to be, if we draw these as similar triangles, so this is still 37 degrees here, which means that this here is T1 cosine of 37, and this here is T2 cosine of 64. So then our Fx is T2 cosine of 64 minus, because this acts in the negative direction, T1 cosine of 37. And that together has to equal our x acceleration, which is 0. And so we have that T2 cosine of 64 is equal to T1 cosine of 37. Okay. Now, our y component from this axis system here, our y component is going to be a sum of coming from all three forces. So here we have T2 sine of 64, and here we have T1 sine of 37. So our Fy is going to be, and both of these are going to act in the positive direction. So T1 sine of 37 plus T2 sine of 64, and then T3 acts downward, so minus T3, and that equals 0. But recalling that T3 we've already solved for is 1225. So then T1 sine 37 plus T2 sine 64 is equal to this 1225 newtons. And then from the x equation, we can solve for, say, T2. We can pick any of them really, but I'm just going to say T2 is T1 cos 37 over cos 64. Plugging this into the y equation, we get T1 sine 37 plus T1 cos 37 sine 64 over cos 64 equals 1225 newtons. Or we can pull the T1 out and completely solve for it. So T1 is 1225 divided by sine 37 plus cos 37 sine 64 over cos 64. So I've just completely pulled T1 out, and now we just have numbers. And so yeah, there we go. So that's just equal to 1225 newtons over 2.2383, which is 547.06 newtons. And then using our T2 equation up here, we can solve for T2. So T2 is T1 cos 37 over cos 64, which is 547.06 times cos 37 over cos 64, which comes out to 996.64 newtons. Okay, now we have our three tensions. So T1 is 547 T2 is 986, and T3 is 1225. Okay, so I don't know if it's because they use 9.81, they're rounding everything to 3 significant digits, which I suppose I should have done, so it would be 1230 with significant digits, 997 and 547. But I would round only at the end because, so here, I guess they're using, I guess this looks a bit simpler to do, but the way I did it is a bit more expanded and shows at least where the forces are all coming from. But you could do it, it looks like either way. The only reason why the values are different is because they use the rounded T3 to calculate T1 and T2, so it expands it a little bit. But so there's just a couple rounding errors, but it looks like the method is correct. Okay. So here we need to estimate the terminal wooden sphere tailing through the air, taking its radius as 8 centimeters and its drag coefficient is 0.5. So here we have an air resistance given by 1/2 C rho air, where that's the density of air, times the cross-sectional area of the object times the velocity squared, where that's our drag coefficient, our density of air, I'm going to take as 5 kilograms per meters cubed. Our cross-sectional area for our object as the sphere is going to be pi r squared, so that's basically a circle, which would be the cross-sectional area. And then v is our velocity, which we're trying to solve for. So our terminal velocity occurs when our downward, our gravitational force is perfectly balanced by our friction, or when so our terminal velocity occurs when our acceleration is 0. So when our friction minus mg is 0, or when our friction equals mg. Our mass can be solved for from our given density for our sphere, times our volume, which for a sphere is our density of our sphere, 4/3 pi r cubed. And so putting these two together, we have 1/2 C rho air times our cross-sectional area, pi r squared, times our velocity squared, is equal to our density of our sphere times 4/3 pi r cubed times g. So this velocity is our terminal velocity. So now solving for our terminal velocity, or solving for it squared, we have our sphere density times 4/3 pi r cubed g, all divided by 1/2 C rho air pi r squared. That r squared is going to reduce that to an r to the 1. There goes the pi, and we can take this 2 and multiply it up. So 8 thirds rho sphere g r over c rho air. Okay, so now we can start plugging in some values. And so this would be 8 times the density of our sphere is 0.830 grams per centimeters cubed. Our g is 9.8 meters per second squared. And our radius is 8.00 centimeters. And we're going to obviously need some unit conversions here. So to convert from centimeters cubed to meters cubed, we need to multiply by 100 centimeters per meter cubed. To convert from centimeters to meter, we need a meter per 100 centimeters. So that'll cancel that one. And that'll cancel this one. And also to get rid of the grams here, we're going to need to multiply by another factor of 1,000, 1 kilogram per 1,000 grams to get rid of the grams in there. And this is going to be divided by 3 times our drag coefficient, which is given as 0.500, times our density of air, which is 1.225 kilograms per meters cubed. So then this gram will cancel with that, this kilogram will cancel with that, this meter cubed will cancel with this one. And then we're going to be left with a meter squared per second squared, which is our speed squared. So then our VT squared is, once we work through all this in our calculator, 2833.07. Or our terminal velocity is 53.23 meters per second. Okay, so we can, so you can, here we just start with an equation, which would just be found by solving this. So exactly what we have here. So plugging in some values with some unit conversions at the top here to get everything into the proper units. And then we get about 53.8, which I assume must be just differences in rounding. Yeah, and I guess I use 1.225 instead of 1.2. So that would just be the difference there. So this looks good. Okay. Here we have a relativity question where we're given the rest mass of a baseball and we're asked to solve for the mass of the ball or the observed mass of the ball if we're moving at 250 kilometers per second. So our mass that we observe is our rest mass over the square root of 1 minus the velocity squared over c squared. We're given that our rest mass is 0.145 kilograms and our velocity is 250 times 10 to the 3 second. So our observed mass is just 0.145 kilograms over square root of 1 minus 250 times 10 to the 3 meters per second squared over 3 times 10 to the 8 meters per second squared, which is the speed of light, which comes out to be 0.145 over the square root of 0.9999993, which just equals 0.1450005 kilograms. So even at 250 kilometers a second, which is very fast, we still only, the observer would only see an additional 5 times 10 to the minus 8 kilograms. So pretty much a negligible change even at that high speed. Yep, looks good. The only thing is, they say the observed mass is in meters per second, but that's fine, it was just a slip. Okay, all right, so here, we have a circular table, which could be drawn better, but it's okay. And it's rotating at 240 RPM. And from the center of the table, there's a spring attached to a mass. And I drew these little lines in because the mass can only move radially with respect to the circular table. The spring constant is given by K. The mass is given by M. Or M. Okay. It can only move radially. The spring constant's K, and the length of the spring is L. So our spring force is minus K, and it wants us to find a relation between the mass and the length D to which the spring stretches while the table is rotating. So our force will be D minus L, where D is whatever length it reaches, and L is its equilibrium length. So our force, and it's negative as it's a restoring force, so a force to bring it back. Now as the table rotates, we're going to get a centripetal force, which must be equal to minus M R, or using omega is V R. Yeah, omega is V R. Oh, V over R, sorry. Omega is V over R. And solving for V, we can plug that in here and get minus M omega squared r. So our restoring force here, which is our spring force, must be equal to our centripetal force, or minus k d minus L is equal to minus m omega squared r. Canceling signs. Now the r here is the radius at which the mass is rotating, which we're given in the problem is just d. So we can put that in. K d minus L is equal to m omega squared d. And it wants us to find a relation between the mass m and the length d to which the spring, I assume the length d in terms of the other terms. So we have k d minus kl is equal to m omega squared d. We can now bring some terms over, so k d minus m omega squared d is kl. Might as well pull d out of here and say k minus m omega squared is equal to kl, or our distance is kl over k minus m omega squared. And we can pull the k's out and write it as L over 1 minus m omega squared over k, like that. And I guess we could clean this, or we could add some numerical values, although I'm not sure what the point is since we're not given any of the other ones. But omega is 240 RPM, which is 240 times 2 pi times 1 minute per second, per 60 seconds. To put it into radians per second, or per seconds, so that our omega squared would be 631.65 per second squared. And so we could then write our d as L over 1 minus m 631.65 per second squared over k. So then that would be the length d to which the spring stretches while the table is rotating in terms of its equilibrium length, the force constant on the spring, and its mass. Okay, so checking here. So our force is given by just kd, which I wouldn't say is quite true, because unless the equilibrium length is purely purely due to d, or if you set the 0 at L, I suppose, but that's not a good idea. But then your R comes out to be L plus D. Now that I think that will give you some trouble due to just moving your origin from the spring to the center of the table. Yeah, I think that would give you some trouble. But it might be solvable that way. Yeah, it should be solvable that way, actually. But then here, I wouldn't say this gives you the relation between the mass and the length d, purely because d is on both sides of the equation, so it's incomplete. So I'd say it's incomplete. D is on both sides of the equation. Not solved free. But would it give you the same thing? Yeah, I think it would actually. Yeah, it looks like it, because you divide by these. I think so. But it's incomplete because it's not solved for D. I'm just going to say it's incorrect. Okay. So here we have two identical uniform solid spheres connected by a uniform rod. And we're given several axes, A, B, C, D goes that direction, E is here, and F is here. And we're asked to rank, oh sorry, D isn't there. That makes more sense. D is through the middle this way. And we're asked to rank the moments of inertia about each of these axes. So remember, our moment of inertia is the sum over masses times distance squared for discrete objects, but for continuous objects we would use the integral. And so the main takeaway here is that it depends on the distance squared to the axis, and we're talking about perpendicular distance here, so it'd be completely perpendicular. So from the d-axis, we would just go straight to the mass point. Say for the a-axis, again, we would go straight to the mass point. So whichever has the highest distance from the axis would have the highest moments of inertia, and whichever has the lowest would have the lowest moments of inertia. And so if we look at our d-axis here, we can see that all the vectors that you draw would be small. And so the d-axis is likely to have the lowest moment of inertia. And if we look at, say, our c-axis here, you can see, although these ones are going to be small, these are going to be quite large. And because it's r squared, you want the distances to be kept as small as possible. So anything with large distances is going to contribute way more than, say, for the a-axis, where you have the same amount of r's, but they're all half as big as for c, where you'd have half of them twice as large. So that means our c-axis is going to be likely very large, and probably our largest, or it will be our largest. And because it's perpendicular distance and this is a 3D object, we would expect, since C goes through the center of a sphere, and F, although it goes out of the page, it's also going through the center of a sphere. So if we rotated this 90 degrees, then really what we'd have is the same looking object, which that's supposed to be the same. the same looking object, but with our f-axis going this way, our a-axis out of the page, our e-axis going this way, our b-axis out of the page, our c-axis out of the page, and our d would still be this way, right? So in other words, f and c look to be the same, and e and a look to be the same. So these two are going to be the same, f and c are going to be the same, and so we can start to rank. So D is going to be our smallest. We already said that C is going to be our highest, and F is going to be equal to it. B is then going to be our next highest because it has the next highest vectors. And so A and E are then our next lowest, as they're both the same. So we've got A equals E. And then that's going to be less than B. And that's going to be less than our C, which equals F. I don't think I missed any. Nope. Okay, so our D's are lowest. A and E are then our next lowest, which bisect the shape. Then B is going to be our next lowest, and then C and F are our highest. Okay, so R squared is our biggest factor, and we did it in the opposite direction, but C equals F is greater than B, is greater than E, is greater than D, so they missed the A, but that's okay. Looks good. And I'm actually going to stop it there and say that's it for today. Thank you for watching. If you enjoyed this, please subscribe to the OneClass channel. If you want to add questions, please follow the links below the video. This has been Jeff Krause for OneClass.